Hello. Today we are moving to chapter 12. Chapter 12 is a short chapter. It's a very short chapter. Um, Chapter 12 is about a regular expression and finite automata. Let me explain what is finite state automata. Finite state automata. This is defined as the simplest machine to recognize patterns. Okay, so this means the simplest machine or to recognize patterns. All right, that is finite state automata. There are some applications of this concept. Those applications are these are useful to design text editors, something like grammar checkers, or things like sequential circuits. All right, the applications are these are useful to design text editors. All right, as an example, grammar checker. Okay, let me rewrite this. Grammar checker. Grammar checkers, sequential circuits. Etc. Oh, give me a second. Sequential circuit give you sequential circuits, etc. All right. So these are the applications of finite state automata. Let's move to the first section. First section is about formal languages and regular expressions. This is part 1 of the section. In the next day, I'm going to teach the part 2. As we learned early, it is good to learn about formal language and regular expressions, because finite automata is used to design grammar checkers or the text editors. All right. So let's learn about formal languages and regular expressions. For that, first you have to define the alphabet of the language that we define on. It could be anything. Our alphabet is A, B, C, D, E, F, G, H up to C. But you could define different alphabets for different languages. Here, alphabet is defined by sigma. Alphabet is defined by sigma. It is a finite set of characters. So, right, you know that. It's a finite set of characters. In our language, it is A, B, C, D up to C. Okay. In English alphabet, let me put a note on that. In English, let me say regular English. In regular English, this alphabet is actually A, B up to C. There are 26 characters. All right. This is epsilon, and then string over this is sigma. String over sigma is 1 is a finite juxtaposition of elements called characters. These elements are called characters. Elements means characters. All right. Of sigma, or the second case is null string. Strings can be null string too. Keep that in mind. It can be null string too. All right. It can be null string too. And then let's talk about length of a string over sigma. The number of characters that made up the string with null string having length 0. Okay, if it's the null string which is having length 0. A null string having the length 0. So the length of the string is a number of characters, okay, in the string. Okay, then formal language over sigma, a set of strings over that alphabet. Okay, set of strings. You know our language, right? Our language is defined over the alphabet A, B, C up to C. All right. Formal. If you just consider the formal language of our regular English, this consists all the words that we are using in daily basis. Okay, all the words in English. That is called the language. All right. All right. We have an example here. Now in this case, alphabet is just 2 letters, A and B. And part A of the problem, define the language L1 over sigma to be the set of all strings that begins with the character A and have the length at most 3 characters. All right, so that is the first part of the problem. And then the second part is a palindrome is a string that looks like the same if the order of its characters is reversed. For instance, ABA and ABBA are palindromes, right? So if you reverse them, they look like the same. Here it is ABA. If you just reverse, then it again ABA. Okay, so they look like the same. And this is, if you reverse them, it is BAAB. Okay, so they are called palindromes. Define a language L2 over epsilon over sigma to be the set of all palindromes obtained using the characters of sigma. Return 10 elements of, write 10 elements of L2. You have write 10 elements of L2. All right, so let's do this problem. All right. In the first part of the problem, you have to define language L1 over sigma to be set of all strings that begin with character A and have the length at most 3 characters. Okay, so you have to begin with A. So L1 will be always begin with A, and just in first case you can put just one A, which is A, and then start with A. Then just consider characters with two strings with 2 characters. It can be A, B, and then consider strings with 3 characters: A, B, and then A, B, A, and A, B, B. Okay, so these are the elements in this language. Let's check whether our answer is correct. I have just put the answer here: A, B, A, like that. This is answer is correct. And then you have to find 10 of these palindromes. You could write any order you want. There are plenty. There are infinitely many such palindromes. So what you have to do is you have to find only 10. Okay, so here I have written down 10 of them. I just write lambda as the first element, which is the string of length 0. That means no string here. This is the string of length 0. All right, so then I have A. If you reverse it, since it's a single element, you can't reverse. If you reverse it, you get the same element. Here the same element. And AA, if you reverse that will be AA. BB, it will be BB. AAA, if you reverse them again, it's AAA. Like that, there are 10 elements. All these are palindromes. All right, so let's move to the next slide. And then we have notations here. We define 3 new notations. First one is sigma to the power n, the set of all strings over sigma that have length n. All right, so now we consider the length. This n is related to the length. The strings have length n. All right, and then we have epsilon plus. This plus refers to the set of all strings over sigma that have length at least 1. The strings have length at least 1. All right, and then is star, that is set of all strings over epsilon. That means sigma. Set of all strings over sigma. Okay, that's the all strings. Okay, now go down. Note that sigma to the power n is essentially the Cartesian product of n copies of sigma. The language sigma asterisk is called clean closure of sigma in honor of Stephen C. Kling. That's the name. Don't worry about this. This clean closure, the name clean is just a name. Don't worry about that. And then sigma plus is the set of all strings over sigma except for lambda, and is called the positive closure of sigma. or the positive closure. There are all the this has all the strings of length greater than or equal to 1. This means all the strings of length greater than or equal to 1. That means it excludes lambda, which is string of length 0. Okay, string of length 0. All right. So let's go to the next slide. I'm going to discuss some examples. And this is example 12.1.2. Here the alphabet is again A and B. You have to find epsilon to the power 0, sigma to the power 0, sigma to the power 1, sigma to the power 2, and sigma to the power 3. And then you have to find A, which is union like this. And then second case you have to find a B, which is union like that. Let me mark this as B. All right. And then you have to just use your words to describe A, B, and then A union B. All right. That's part B. Part C, describe a systematic way to write. Systematic way of writing the elements of sigma to the power plus. What change needs to be made to obtain elements of sigma to the power asterisk. All right, so these are the problems given to you. All right, the first case you have to find sigma to the power 0. I have written down them in the next slide. Let's move to the next slide. Sigma 0 is the string that has 0 length, that means no length. That is simply epsilon. Sorry, that is simply lambda, which is used to define a string of 0 length. The string of 0 length. Which is lambda. And then you have to find there are two equal signs. Then you have to find sigma to the power 1, that includes strings of length 1. So there are two strings that you could think, A and B. And then it is sigma to the power 2, which includes strings of length 2. Those can be AA, AB, BA, BB. So these are easy things, so I don't spend much time. And then a string of length 3. Those are AAA, AAB, ABA, ABB, BAA, BAB, BBA, BBB. All right, so those are the strings. And then in the next problem, A is sigma 0 union sigma 1. All right, so this includes strings of no length and strings of length 1. So A is actually, you have to write A and B in terms of words. you have to just explain in your words what is the meaning of A and B. A is the set of all strings over sigma of length at most 1. Okay, at most 1. At most 1. At most 1 means 0 or 1. And then B is like this. B consists of strings of length 2 and 3. Okay, strings of length 2 and 3, strings of length 2 and 3. And then you have to write A union B in your words. A union B means union of the first case and the second case. That means union of this and that. That means the first case is length at most 1 and then length 2 or length 3. When you combine them, it is length at most 3. When you combine them, it is length at most 3. That is A union B. All right. Just go to the part C. Part C, describe a systematic way of writing the elements of sigma plus. Let me refresh what sigma plus is. Sigma plus is the set of all strings over sigma that have length at least 1. Length at least 1. That means the upper bound is not mentioned. It can be any length. Okay, it can be, length can be, let me see. Length can be increase. Length, let's say length can increase infinitely. All right. Okay. The elements of sigma plus can be written systematically by writing all the strings of length 1. First you have to consider strings of length 1 and then strings of length 2 and so on. Okay, you have to first write in strings of length 1, strings of length 2 and so forth. Okay, which is written right here. It doesn't stop. You have to keep on writing until you are done with everything. There are infinitely many, so you can write everything. So you just write few of them and then what do? You just put these dots to show it is not the end. Okay, these dots represents continuation. Okay, it represents continuation. Okay, now the next part of the problem is what change needs to be made to obtain elements of sigma asterisk. See, sigma asterisk includes 0. Okay, that means sigma asterisk is set of all strings over sigma. That means all strings means including the strings of 0 length. Okay, including strings of 0 length. Of course, the process of writing the strings in sigma plus would continue forever because it is an infinite set. Okay, the only change that needs to be made to obtain sigma asterisk is to place the null string. at the beginning of the list. Okay, you only have to include the null string to sigma plus. All right, that is the end of the example, and let's move to the example 12.1.3. Here we are going to learn Polish notation. Polish notation, that means a language consisting of postfix expressions. Polish notation means language including postfix expressions. All right, that refers to Polish notation. An expression such as a plus b, in which a binary operator such as summation, this summation is the binary operator, sits between the two quantities on which it acts. It's said to be written in infix notation. So that format is called infix notation. If this plus sign stays in between a and b. All right, that you already know. Alternative notations are called prefix notation, right, and postfix notation. Prefix notation means in which the binary operator precedes the quantities on which it acts, and the postfix notation is in which the binary operator follows the quantities on which it acts. All right. When it is prefix notation, operator precedes the quantities. When it is postfix notation, operator follows the quantities. Okay, keep that in mind. In prefix notation, a plus b is written as, you just bring this plus sign in front. Okay, you just bring this plus sign in front, that appear here. In postfix notation, you bring this plus sign at the end, so it will appear here. All right. All right. Prefix and postfix notations were introduced in 1920 by the Polish mathematician Jan. This is the last name, it is hard to pronounce. You pronounce that as Łukasiewicz. All right, so that is the person's name. Just call him by the first name Jan. In his honor, and because some people have difficulty pronouncing his name, they are often referred as Polish notation. That's how the name comes, all right? Since it's a Polish person who discovered that, then this notation is called Polish notation. Okay. And reverse Polish notation. Reverse Polish notation means the thing other way around, like this. All right, see, this is preceding one and the following ones. Those are the two types, prefix and postfix. All right. A great advantage of these notations is that they eliminate the need for the parentheses in writing arithmetic expressions that we are going to learn very soon. All right, now let's consider this. If the expression a plus b times c in infix notation is converted to a postfix notation, the result would be a times ab plus c dot. Okay, so that is the corresponding notation for this. Okay, if you write that in postfix format. If you write that in postfix format, that means the operator comes next, not at the beginning. Operator comes next. A plus a b, and then A, B, and then plus, and then C dot. Operator comes next. If the expression A, B dot C, D dot plus in postfix notation is converted to a infix notation, what is the result? Okay, so you have to find the result of that. It is easy. So this can be written down as A dot B, you could put a parenthesis, and C dot D, and then in between there should be the plus sign. Okay, if you need, you can just forget about these parentheses because they are not important. So this is the corresponding postfix notation. Sorry, in the infix notation of the given postfix notation. Let sigma is for 1 plus minus, and let L is the set of all strings over sigma obtained by writing either a 4 or a 1 first, then either a 4 or 1, and finally either a plus or a minus. List all elements of L between braces and evaluate the resulting expressions. Okay, this is easy, that I'm going to explain in the next slide. So this is the solution for the first part. This is the solution for the first part, and that is the solution for the second part. Okay, so you have to keep 401 at the beginning. Okay, you have to keep the 401 at the beginning, and then you could keep plus or minus. First you could try 4-1, okay, and then plus 4-1 minus, then 1-4, 1-4 plus, 1-4 minus, 4-4 plus, 4-4 minus, 1-1 plus, 1-1 minus. Those are the only possibilities in this language. All right, so this is the first expression, second expression, third, fourth, fifth, sixth, seventh, eighth. There are 8 expressions. Now you have to evaluate them. All right, 4-4 plus means 4-4 plus means 4 plus 1, which is 5. 4-4 minus means 4 minus 1, which is 3. 4-4 plus again, 1-4 plus means 1 plus 4, which is 5. 1-4 minus means 1 minus 4, which is minus 3. 4-4 plus means 4 plus 4, which is 8, and so on. So this is easy. You can understand what are these expressions. All right. Now let's move to the next slide. The following definition describes way in which languages can be combined to form new languages. You know that, right? So in this world, there are some primary languages. At the same time, there are some secondary languages which are made by combining primary languages. All right. Nowadays, it is very hard to find primary languages. But still there are some primary languages, only a few primary languages. All the other languages are made by combining by combining 2 or many primary languages. You know that. Okay, that's why if you go to Germany, they have their alphabet has English letters. If you go to France, their alphabet has English letters. That's because there's an influence between languages. One language borrow some letters from the other language, not only letters but also words. All right, you know that. So these are the definitions. Let sigma be an alphabet given any string x and y over sigma. The concatenation of x and y is the string obtained by writing all the characters of x followed by all the characters of y. For any language L and L prime over a sigma, three new languages can be defined as follows. The first language is the concatenation of L and L prime, which is given like this. That is x times y, where x is from L, y is from L prime. And then union of L and L prime, denoted by L union L prime, which is set set of all element x such that x is from L and also x is from L or x is from L prime. Okay, this x can be from L or it can be from L prime. That is called the union of L and L prime. And then finally we have clean closure of L, denoted by L asterisk, is defined like set of all x. X is a concatenation of any finite number of strings in L. So you are allowed to concatenate any finite number of strings from L. Okay, so that is defined as the clean closure of L. All right, so this is all about definitions. Just go to the next slide where we discuss an example. Let L1 be the set of all strings consisting of an even number of A's, namely, these are the even number of A's. This means no A. That means 0 is an even number. Keep that in mind. What I want to tell is length is 0 since 0 is an even number. Okay, 0 is an even number. That means lambda AA, 4A's, 6A's, 8A's, and so on. And L2 is like B, BB, BBB. Okay, those are the two languages given to you. And then part A of the problem, you have to find L, L1, L2, and then L1 union L2, and then finally clean closure of L1 union L2. So those are the three things you have to find. Then here there's a note. Note that null string lambda is L1 because 0 is an even number. Okay, so I wrote it above. Okay, let's go to the next slide. All right, now L1, L2. This is easy because you could just follow this definition. You could just follow this definition to write it. This is actually the set of all strings that consist of an even number of A's followed by B or BB or BBB. All right. This is, give me a second. This is from, this part is from L2 and this part is from L1. All right, even number of A's, which is L1. L2 consists B, BB or BBB. All right, so that's clear. Now go to part B. Now you have to find L1 union L2. Is the set that includes the strings B, BB, BBB. That means L1 and any string consisting an even number of A's. Even number of A's, which is L2. I'm sorry, I made a mistake. This is L1, that is L2. All right. And finally, you have to find the clean closure of L1 union L2. The clean closure is defined here. Clean closure, that means it consists concatenation of any finite number of strings of in L. It's any finite number of concatenations. Okay, so it can go up to infinity. All right, so then what, you already know this. You already know that part without the clean closure, which is part B, which you found in part B. So this part is already found. This is part B. Now you have to get the clean closure of part B. Okay, it is the clean closure of part B. Okay, that is the set of all strings of A's and B's in which every occurrence of A is in a block consisting of an even number of A's. Right? It's a combination of A's and B's, but if it has A's, then they should be blocks of even numbers. That's how L1 happens. Okay, that's how L1 happens. Give me a second. A in blocks consisting of even number of A's. Okay, that means L1. L2 says B, 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 B. But here you are concatenating any number of occurrences. So if you concatenate B with BB, it will be BB, BB. If you concatenate BB and BB, it will be BB, BB. Okay, there are all the possibilities. That means that there can be any number of B's, because by just B, BB and BBB, you can make any number of B's if you concatenate them, odds, evens, and everything. So that's why in part C, we do not talk about B somewhere, because B can be anything. Like it can be single B, two B's, three B's, at the beginning, at the middle, at the end. But if it has A's, then A's should be even numbers, because it occurs as even numbers. Even number concatenated with even number, again an even number. So this should be preserved. They should be even numbers. All right. So that is the end of the first part of this section. I will start this next part of the section next day. Thank you very much.